Okay, it is my privilege and honor today to introduce Sarita Adve. She's going to talk to us about some work that she's been doing on and off, again, I guess, since I knew her in graduate school maybe 20 years ago or something. Sarita has been working on many things from reliability. She is one of the people that defined the notion of a memory model. Prior to Sarita's work, we didn't really have a good idea of what it meant to order accesses to a shared memory. And Sarita's work is the canonical work that we point everyone to these days. She's an ACM fellow. She serves on the board of the Computing Research Association. She has also won the Maurice Wilkes Award, which recognizes outstanding, not beginning and not late career, but mid-career computer architects. Got to get the right phrasing there. And Sarita is going to talk to us today about her view of how we should handle programming parallel systems with the pendulum swinging towards multi-core processors, again now in lots of activity in that space. So I'm going to let Sarita take over from here.
Thank you, Ali. Okay, now that I'm firmly established as a mid-career person. Okay, so the title of my talk is Rethinking Parallel. Oh, there's an echo. Okay, so the title of my talk is Rethinking Parallel Hardware and Parallel Languages. And this is work, as Avi said, I've done over the course of, or the talk will describe work that I've done over the course of about 2 decades. With lots of people. So this is a list of many people that I've worked with. It's a partial list. I'm going to start a little bit with a more general motivation for the kinds of things that I do in my group. The main technology drivers really come from, well, Moore's law. It's kind of incumbent on a computer architect to start a talk with Moore's law. So here I go. Moore's law continues to give us increasing number of transistors, but the problem is there are many problems. There's the power problem, as I think we all know in this room. We get more transistors, but they are flakier than ever. There's a reliability problem. Supposedly, the solution to this all is multi-core. But multi-core comes with problems of its own, in particular programmability. We don't really know how to program multi-core systems very well. And even performance. We really don't know how to build multi-core hardware in a performance-efficient way for the kinds of programs that we write. So in my group, I have 2 main projects going on. The first one is SWOT, and that addresses the reliability aspect of these technology drivers. We are working on a very low-cost hardware reliability solution where we treat hardware faults like as if they were software bugs. Okay, so it's a sort of a new take on how to do hardware resilience, but I'm not going to be able to talk about this too much. What I will talk about is the de novo project that I'm leading. It's essentially rethinks multi-core hardware design for discipline parallelism. It's driven by a software project, a programming languages project led by Vikram Adve called Deterministic Parallel Java that provides us with a safe way to do shared memory parallelism. And the hardware exploits this way of programming. And I'm going to spend a bunch of time talking about de novo and DPJ, but before that, I'm going to talk about this concept called memory models that I've worked for many years now and was the inspiration for the de novo work. Okay, so what do I mean by memory models or memory consistency models? Well, we have parallelism for the masses here, right? So everyone, not everyone, but programming has really become synonymous with parallel programming, right? We want people to know, we want our undergraduates to understand parallel programming. And for better or for worse, shared memory is by far the most common way by which by which programmers write parallel programs, at least on the client side. So programs written for our desktops, laptops, handhelds, etc. Shared memory threads are by far the most common thing. So what the memory model tells us is, for a shared memory program, what are the legal values that a read in this program may return? Okay, so this is a very, very fundamental concept, right? What value should a read return in your program? And the first time you talk about a memory model and everyone's like, yeah, makes sense. Okay, few more minutes and people go, huh? What? And then frustration, more frustration, and then, oh, just don't talk to me about it, go away. Okay, that's often sort of the way in which the reaction unfolds when you talk about memory models. Okay, so why is that, right? Why is that? Memory models, after all, are at really, what value a read should return is at the heart of concurrency semantics, right? This is what defines what the meaning of a program is. There has, for various reasons, been a lot of confusion surrounding this. And I started working on this about 20 years ago, and it's been a really long journey from this very confusing state of the world to now finally where we have some convergence on what these things mean and what the right solutions should have. And along the way, we learned some very difficult lessons, and I hope to share those with you today. And more important, there are very significant implications for how we design software and hardware moving forward, given these lessons that we've learned. So I would like to share these with you today. And one of the main lessons that we learned really is that the current way in which we define memory semantics is just way too hard. Okay, it's just way too hard. In fact, I will go so far as to say that it is fundamentally broken. Okay, so what we really need is we need to step back and really rethink how we do parallel languages and parallel hardware. Okay, and so I will spend the first half of my talk convincing you, hopefully, that this is a hard problem and we really need to rethink what we are doing. And then hopefully the latter half, I will give you my approach, our approach that we've taken at Illinois, both from the software side, which is the deterministic parallel Java project, and the hardware side, which is the de novo project. Okay, so we'll see how far we get. Please feel free to interrupt me with questions. Okay. And this is both for people here and those listening remotely. So the outline of my talk is going to be as follows. I'll talk a little bit about memory models. I'll talk about what the desirable properties are. I'll talk about the original early work that I did on data race-free models and how these were applied to real languages like Java and C++, what happened for those languages, and the current status. Okay, and then I will talk a little bit about deterministic parallel Java. That will be just a brief overview. Hopefully get into some details on de novo and then conclude. Okay, so let's see what this whole thing is about. What is a memory model? As I said, it says what value a read can return. Okay, that's a simple thing. So this is your canonical example here. You have two threads, 1 and 2. Thread 1 is writing to two variables, a equals 26, b equals 90, sets a flag. Thread 2 reads the flag, waits until the flag is set, reads b, reads a. You ask most people what value the read of b and the read of a should return. You ask an undergraduate, smart undergraduate from Duke, and they'll say, well, it should return 90 for b and 26 for a. Unfortunately, it turns out that many machines today, you could actually get the value 0, okay, the initial value, right? So the reads are not returning the expected values, okay? So this property that tells us, what value these reads should return, what values they could return, is what I mean by the memory model, all right, okay? So as you can see, this is really key to concurrency semantics, right? You can't say what value a read can return. You can't decide whether it's 26 or 0. Well, how are you supposed to reason about your program? So another point I would like to make is that the memory model is really an interface property. Okay, it's an interface between the program and anything that transforms the program. So in this case, for example, I have a C++ program in this picture. It's being transformed by a compiler. So the interface between this C++ program and the compiler has to respect the memory model that is specified by the C++ programming language. Okay, the compiler produces an assembly language. Well, the dynamic optimizer or the hardware that transforms or that works on the assembly language needs to respect the memory model that the assembly language is saying that it needs to maintain, and that model has to be compatible with the C++ memory model. Right? And so the weakest system component is what is exposed to the programmer. And by that what I mean is that if my C++ programming language says, oh, I have a really strong memory model, the values that a read can return are really constrained. You know, these are the only values it can return. But if my hardware or on the other side says, oh, you know, I have a really weak memory model and I'm going to just do whatever I want and give you a much broader set of values, well, that doesn't really quite work because the C++ program and the hardware are out of sync. Okay? So the weakest component really gets exposed. And the language level model has implications on the hardware and vice versa. Okay? The other important thing is that this interface needs to last beyond trends. It's like, you know, it's like an ISA, an instruction set architecture. It's an interface property. It's going to stay with the language or with the hardware forever. Okay? So you know, given that, now what are the desirable properties of a memory model? Right? So the first property, of course, is it should be easy to program because it affects the programmability. Right? It affects how I reason about the program. Second, it also affects performance because it affects the optimizations that a compiler or a hardware can perform because it constrains those optimizations. Third, it affects portability, right? I can take you know, I want to be able to take the same C++ program and run it across different hardware. I want to be able to get the same answers, right? So I call these the 3P properties. Performance, you know, we want easy to program, high performance, and high portability. And the reason why this whole issue has been so problematic is that it has been really hard to come up with a memory model that satisfies all these 3P properties. Okay, so in the late 80s to the 90s, this whole area was largely driven by hardware people. Okay, there were lots of models. Every machine had its own model. There was very little consensus. 2000 onwards, programming language people, compiler people started thinking about this problem some more, and a lot of the action came from there, and a consensus model developed for Java, for C++. It's still ongoing. C is ongoing, but there's now a consensus. Okay, and these programming language efforts then had to deal with a mismatch between what the hardware was doing and what the language people wanted to do. Okay, so today, the next part of the talk, I'm going to talk to you a little bit about the path to the convergence. Okay, how did we finally converge to this consensus Java and C++ model, and what are the lessons for the future? All right, so questions at this point? Is this relatively clear? I'm not sure what the backgrounds of the people here are. You know, please feel free to ask questions. Okay, so let's talk about programmability. Now, this is one place where there has been some consensus. Okay, and even here, some purists will debate whether this consensus is reasonable or not. But one place where we do have consensus is that a model called sequential consistency is really the simplest for programmability. Okay, most people will sort of buy that. And what this model says is that, well, the memory operations of a single thread happen in program order, in the order that is specified by the program, and the result of the multi-threaded execution is as if there was some interleaving of these multiple threads, some sequential interleaving. Okay, so individual threads work in program order, and there is an interleaving, which means that individual operations are all atomic and happen in some sequential order that's consistent with this program order. All right. However, the problem with sequential consistency is that there are many performance optimizations that are hard to implement with sequential consistency. Now, a lot of smart hardware people have come in and shown how you can do some hardware optimizations without violating sequential consistency, but compiler transformations are still inhibited by sequential consistency, and so it's generally widely believed that there is a performance problem here. Okay. Regarding portability, well, it turns out today all hardware, all compilers, or I should say, most, to my knowledge, all hardware and compilers violate a sequential consistency today. Okay, so sequential consistency as a memory model is not practical today. Okay, however, what we can do is provide the next best thing, okay, which is almost always sequential consistency. So what do I mean by that? So the insight here is that parallel programming is hard even with sequential consistency. So even if I gave you a sequentially consistent system, okay, programmers still make mistakes, still write buggy programs, and that's still not enough to write good code. So programmers want to write well-structured code, code that has no data races, that has explicit synchronization, and it turns out that for such code, it's actually easy to give sequential consistency and high performance. Okay, so for example, here's a piece of code where I have two threads that are trying to access two data variables, and they access them in locks, right? So if the hardware or the compiler knew that this was a lock access, a synchronization access, then it turns out that the hardware or compiler can actually reorder the data accesses between synchronization, do crazy stuff between synchronization. As long as sanity is restored at the synchronization point, we are fine. We do not violate sequential consistency, and that's not terribly hard to prove. Okay, so it seems then that that if programmers write such programs where the synchronization is explicit, then we can get easy programmability, namely we can get sequential consistency and we can get high performance. Okay. And what I did in my PhD thesis work a long time ago was to formalize the notion of what do we mean by well-synchronized program. And that formalism, we call that the data race-free model, and I'll talk about that in the next slide. And the model says that for data race-free programs, the model will give sequential consistency. Okay. The catch is that if your program has data races, then there are no guarantees. Okay, so that was a model that we proposed in 1990. Okay, so this came from academics. Let me give you a little bit more detail on what I mean by this model, and then I will talk about what the practical implication of this academic model was. Okay, so the idea is that we are going to have data, we want to give semantics only to programs that have no data races. So this begs the question, what is a data race? Right? And intuitively, I think we all know what a data race is, but surprisingly, the meaning, when you ask people to formalize the meaning, there are different definitions. So here's the definition that we came up with. It's a very simple definition. The first concept is that we would like to be able to distinguish between different sorts of accesses. Okay? So somehow the language, the hardware has to give us the ability to distinguish between data accesses and synchronization accesses. Okay, data and non-data accesses, and we can just think about them as green accesses and red accesses, right? Use whatever way you want to distinguish them. Okay, and the other thing is that because we want programmers to only be able to reason with sequential consistency, we don't want programmers to reason with crazy memory models, we would like this definition to require thinking only about sequentially consistent executions. Otherwise, if I have to think about crazy executions, non-sequentially consistent executions, then that sort of defeats the purpose. So with sequentially consistent executions, I have a total order, right? That was the definition. So now what I say is that two memory accesses, they form a race. If they come from different threads, okay, they're to the same location, and at least one of them is a write. So it's a very simple definition. Okay. The key is that they form a race if they occur one after another or consecutively in this execution. So what do I mean by that? Well, here's that example again with write of A and write of B, right? The example where we weren't sure whether we should return 26 or 0 for the read of A. So in this example, you have the two data writes, which are green. You have the red access, which is the flag write, and then the flag read on thread 2. And then you have the two green accesses. Now, in every sequentially consistent execution, okay, the green accesses, okay, that are in different threads, right, thread 1 and thread 2. If you look at write of B and read of B, they are from different threads. They are to the same location. One of them is a write. Right? These two write of B and read of B, they are potential candidates for races. However, they never occur right one after another. They're always separated by the red write of flag and read of flag. Right? So that's a really important concept. Okay, so if they're always separated by this write of flag and read of flag, then we say that they can never race. So these are not races. Okay, whereas the write of flag and the read of flag, the red axes, come one after another. Okay, and one of them is a write. They're on different threads, and they're both to the same location. So these axes form a race. Okay, and what we require the programmer to do is to say that a race, okay, with a data access, okay, is what we call a data race. Okay, and you're not allowed to have data races. In other words, all the races need to be colored red. All the races need to be flagged as synchronization. Okay, so there are no data races in your program. Okay, if you have green axes, they can never come one after another. Okay, that's the simple basic requirement for a data race-free program. All right, make sense? Yeah. Okay, so a data race-free program is a program where there's no data race in any sequentially consistent execution. Okay. And then what the data race-free model does is it says that if you write a data race-free program, which is well defined, then this system will give you sequential consistency. Okay, so write data race-free programs, get simple programmability with sequential consistency, and get good performance. Okay, note that this does not preclude the use of races for what are called weight-free constructs. So if you're not familiar with those constructs, great, good for you. Forget about what I'm saying. But if you are familiar with those constructs, don't worry, we do allow them with this model. Okay, you can do whatever crazy things you like as long as you just color all of the races as red. Okay, or you call them synchronization. In real life, in real languages, you can't color things as red or green. Instead, for Java, you have the keyword volatile, so you use volatile to identify variables that might race. In C++, in the new upcoming C++ standard, you use the word atomic to identify variables that might race. Okay, and so this is Decker's algorithm. For those of you who've never seen this, I hope you never get to see it again. But for those who do know about it, this is how you would do it. You have this is the core of Decker's algorithm. You have two threads. The threads are writing and reading to flag 1 and flag 2, and there is a race here between the flag axes. This is just fine as long as in Java you say flag 1 and flag 2 are volatile, the races are fine, you will get sequentially consistent results, and this algorithm works. Okay, so that's the idea behind the data race-free model, and the reason why this all makes sense again is because you get programmability because you're talking about simplicity of sequential consistency for data race-free programs. For performance, you're specifying very minimal constraints. You just give SC for data race-free programs. You want SC, you want to write data race-free programs, that's all the system has to ensure. And for portability, the language needs to identify, needs to provide a way to identify races, and the compiler needs to make sure that it can translate those particular race operations into something that the hardware understands as being racy and that it has to protect. Yeah?
Doesn't the execution of Decker's algorithm itself constitute a data race?
Yeah, exactly. So it's not a data race, right? So the point is that there is, so the way I like to think about this is that there is a race between the flag operations, right? And if I color the flag operations red, then they become synchronization operations. So there are no data operations in this code, so there is no data race.
So you're explicitly marking the locations that are used as synchronization variables.
And the way I do that in Java here is by saying volatile flag 1, flag 2.
Saying races will occur only on these variables.
Only on volatile variables. Okay, so the way you translate the notion of race, non-race in Java is all variables that are volatile may be involved in a race. Variables that are not volatile are proclaimed by the programmer to not be involved in a race.
And that means that conflicting accesses will have an intervening access to a synchronization variable?
Yeah, so if the programmer indeed wrote a data race-free program, then non-volatile accesses by definition will always be separated by volatile accesses. That's what it means. Now you can ask, but the programmer may not write a data race-free program. The programmer may forget to put that volatile declaration, in which case that becomes a buggy program in this model, And then this model gives no semantics whatsoever, which goes to the heart of the problem that I'm going to describe next. Okay? All right. Okay, but in theory, this was the model. This model is what we proposed, and it seemed to make sense. Okay. So this is what happened. This is what we were doing in academia in the early 1990s, figuring out what optimizations would be allowed for such a model, what hardware can be used, et cetera, et cetera. In practice, what was going on at that time? Well, in practice, the hardware folks, okay, people in industry, were mostly coming up with memory models that were driven by a more implementation, or what I call a performance-centric view. Okay, as opposed to a more programmer-centric view, which is what I, would like to characterize the data race 3 model as. So different vendors had different models, right? Most of them were non-sequentially consistent. There was a different model for Alpha, Sun, x86, which actually didn't really have a model to speak of, Itanium, IBM, AMD, HP, Cray. They all had different things. Okay. And the way these models were described almost uniformly were in terms of ordering requirements between memory accesses of a single thread. Okay, so in this case, I've shown this model. The arrows that I've shown there say that a load followed by a load will be ordered. Let's say, okay, the next arrow says that a load followed by a store will be ordered. And if the model said that wanted to say, well, some of the models say, well, if there's a store followed by a load, no ordering guarantee is given. Okay, there's no guarantee. Instead, the model provided a notion of a fence, some form of a fence instruction, and if the programmer wanted a store followed by a load to be ordered, the programmer had to insert that fence. And you might say, well, that seems like reasonable. But these fences came in all sorts of flavors, and there were many, many subtleties that made it really hard to understand what they really meant to accomplish. And even experts, you'd give them example programs and say, where should I put fences here? Will I get a 0 here or a 1 there? And they'd say, oops, I don't know. Okay? So this was the backdrop. This is what was happening in the hardware world. Right? Many, many ambiguities. The high level in the languages area, well, most shared memory programming was done with pthreads and OpenMP. And these are really libraries. These are not languages, right? These are not, this is not part of a language. The compiler doesn't know about these things, right? So, and even for these things, the specs for the memory model that these things had associated with them were incomplete and ambiguous. And Hans Bohm has a really nice paper in PLDI 2005 that talks about why the memory model really needs to be the property of the language and not a library, because to first order, the compiler needs to know about what the memory model is, right? So Java was the first commercially successful language with threads. There was Ada that came way before it, but Java was really the first commercially successful language with threads. And if you have threads in your language, you have to have a memory model. Okay, so Java had a chapter in the Java language specification book on the memory model. However, it was really hard to interpret this chapter, and it turns out that many things were badly broken. So in about 2000, Bill Pugh from University of Maryland publicized some fatal flaws in the Java memory model and lobbied Sun to form an expert group to revise the Java model. And really, it's from this point that the programming language community kind of was, I would say, energized. There was work done even in the past, but this was in some sense a turning point in terms of just the awareness of the problem. And the whole effort to revise the Java memory model, it was done by an open mailing list process. There were diverse participants from hardware, compilers, OS, software engineers, all sorts of computer science, computer people, developers, researchers, academics, industry people, etc. It took 5 years of really spirited, a lot of debate as to what the model should be, many competing models, and eventually, finally, after a lot of work, a consensus model was adopted and blessed. Okay, so this was in about 2005, and this was what came out for Java 5.0. So what are the highlights? Well, in this 5-year process, the first thing that people agreed on really quickly was that for data race 3 programs, we need sequential consistency. No debate about that. Okay, so that was about the last part where there was really clear consensus. Okay, but there was a missing piece here. So data race-free model is great if you write data race-free programs, right? But how many programs do you know that don't have bugs in them? Okay, many real programs have bugs, and many of those bugs are data races. So a model that says that there are no semantics to a program without that has a data race in it doesn't quite work with Java, because Java is a safe language, and in a safe language you have to have some semantics for every program. Okay, and it turns out that to ensure the safety guarantees of Java for programs that have data races was very, very hard. Okay, it was hard because nobody really understood what it means to have safety guarantees for a parallel language. Okay, all we know is that, well, you can't really, you have to somehow limit the damage that data races can cause, right? So for example, with Java, you could bring in some untrusted code, and that code could have a data race, and that malicious data race could muck around with your stuff and start producing all kinds of crazy outputs, and Java doesn't allow that. Okay, so our goal really was to satisfy the security and safety features of Java. But at the same time, nobody wanted to give up performance for racy code, right? We know races are bugs, races are bad. We do not want people to use races, so we do not want to give up any performance for racy codes. But at the same time, we have to give some semantics to racy codes, because we don't want those racy codes to go and mess with the code that we wrote that is not racy. Okay, so the problem was that, well, what is the safety and security thing? How do we limit damage from the data race? It just was all very, very vague. And I'm going to, in the interest of time, unless somebody has a question, I'm going to skip the example, and just quickly just take a leap of faith here and say that after a lot of back and forth trying to figure out what is meant by safety and security and how do we limit the damage, how do we reduce performance impact, there was a final consensus model, but it is very, very complex. Okay, and the sad thing is that the complexity comes about because of programs that are supposedly buggy, right? So the bottom line is that for this model is that programmers can and must use SC for data race free. However, system designers have to deal with the complexity, because the system designers have to make sure that their system obeys the Java model for all programs, right? Moreover, correctness tools and debuggers and so on need to deal with the complexity, because they have to, again, work for all programs, right? So turns out that not only is this model extraordinarily complex, but a few years ago people discovered bugs in this model, not surprisingly. Okay, given the complexity, I mean, it's not surprising that they discovered bugs, and also not surprisingly, these bugs remain unresolved. Okay, so the Java memory model is much, much, much better than it was in 2000, but it's still broken. Okay, so that is the status of the Java memory model right now. Okay, very complicated. Sort of does a reasonable job, but really still broken. Okay. So then in about 2005, the C++, Hans Bohm, who worked with us in the Java memory model as well, he started an effort to fix the C++ memory model. Well, not just to fix it C++. C++ at that time didn't really have threads as sort of first-class objects, so there's this whole effort to specify some, the threads and so on for C++, including the memory model, and Microsoft started its own internal effort and so on. And it turns out that C++ actually should be easier than Java in a sense, because it's unsafe, right? C++ already has these, lots of cases where there are no semantics, right? So we should be able to take data race tree and say, okay, data race tree works. You have no semantics for these things. You have no semantics if you have races, right? And Bruce was kind of, okay, how can C++ ever be better than Java, right? When you saw my slide, and this is how, All right, it's better than Java for the memory model because it's worse than Java for everything else. Okay, so the data race tree should have been a plausible model. But there was another twist. It wasn't the end of our struggles because around this time, multi-core came along, okay, where there were new hardware optimizations being done. There was more scrutiny, and it became very obvious, painfully obvious at this time that the hardware way of dealing with memory model is quite mismatched with the programming view. And essentially, the core of that is that fences, they define really per thread order, which is what the whole hardware model is based on, whereas a memory model, really things like synchronization and so on, define ordering between threads. So there's this per thread view and there's the inter thread view, and they don't always match up. And so that creates problems that I don't really have time to go on in much detail, but there was a huge debate for the longest time that sequential consistency for data race 3 was just not possible. It was just too inefficient to implement on current hardware systems. Okay, so that even for C++ we couldn't use this. Well, to cut a long story short, I'm not going to go through these examples. There was a lot of pressure on us to change the Java and C++ memory models to remove sequential consistency as a baseline. Okay, so a lot of hardware vendors were saying that we can't really do this. But after a lot of work and evangelization and so on, we saw that the kinds of things that the hardware people wanted to do, yeah, they may give you better performance, but nobody could come up a way to describe them, okay, to put semantics on them in a way that we could, that would be screwable to undergraduates, for example. Okay, it was just too hard. Okay, so we showed that probably such a model doesn't exist, where you take away a sequential consistency as a baseline, try to incorporate these optimizations, and it's still simple to teach. And so finally, there was a compromise, and the default C++ model is still data race free. Most hardware vendors were on board, but some systems would still need some expensive fences to do this. And so for those systems, C++ has a lower level model that allows you to do some crazy things that have a complicated specification. It's only for expert programmers. We're not advertising this part, right? I'm not going to tell you anything about this because I don't want you to use it, okay? But we had to do it, all right?
Gives you a monopoly on being an expert.
No, it doesn't actually, because I refused to do that. So Hans did that part. So what? Because I'll tell you why. Because I think this is all totally broken, and we just need a different approach. And Hans was kind of stuck because he had to get the thing passed through the standards, and so he actually did a great job. It was just amazing that he got this to work. Yeah. It's the same reason why I don't want to solve the Java memory model bug. Okay, so the convergence to SC for data race 3 as a baseline, where the status is that for programs with data races, for programs without data races you get SC, with data races you get minimal but complex semantics for safe languages, no semantics for unsafe languages. So lessons learned are SC for data race 3 is the minimal baseline, but specifying semantics for programs with data races is really, really hard. Okay, that's really the bottom line that came out from this thing. But the problem is no semantics for data races also has problems. And it's not an option for safe languages. You can't do debugging. Correctness checking tools need semantics. And then hardware-software mismatch for some code, right? I didn't show you these, but simple hardware optimizations had unintended consequences. They broke the simple data race 3 model. So these were the lessons learned from this 2 decades of work in this area. And my conclusion is that the state of the art is really broken. Okay? If you cannot specify what value a reader is going to return in your language, what good is that language? Okay, this is really not a good state of affairs. Okay, so at this point, right, the obvious question is, get rid of shared memory, right? Okay, that's a reasonable suggestion. But what I would like to say is the problems we have with shared memory today are really not fundamental to shared memory per se. what the problems are because of what I call wild shared memory. And instead what we need is a more disciplined form of shared memory. I'll tell you what I mean by that. Okay? So what we need is a higher level disciplined programming models that enforce this discipline, and then we need hardware that's co-designed with these high level programming models. Okay. So what do I mean by this discipline? Okay. So let's step back for a second and ask ourselves, well, what really is the meaning of shared memory? Right? What is it that we really want to get out of shared memory? Well, shared memory is a global address space. This is what programmers really want. This is what they care about. Okay, this is why it's important. But unfortunately, shared memory is also implicit, anywhere communication and synchronization. And that is the wild part. Okay? The part that's, the global address space is the good part. The anywhere implicit communication synchronization is what I call the wild part. That's what we want to get rid of and instead replace it with a model that has explicit structured side effects. Okay? All right, so that's our plan. What is the benefit? What do I expect to be the benefit of these explicit structured effects? The cool thing, at least to me the cool thing, is that there are benefits from both the language side, the programming side, and the hardware side. And they're sort of independent, or they're like independent of each other. From the programming side, I will show you that having these explicit effects, and I will tell you in more detail what I mean by explicit effects, but you can imagine having explicit side effects can allow you to develop languages that have very strong safety properties. So for example, I will show you not only can we get rid of data races and get rid of the whole memory model problem, we can also have languages that provide us determinism, okay, which is a very, very strong safety property. In particular, determinism allows us to reason about a program like as if it were a sequential program. It allows us to test a program like as if it was a sequential program. It gives us modularity, it gives us composability, and all sorts of cool things. Okay? So I'm going to show you the project that we are doing that gives us determinism by default semantics through these side effects, through these explicit side effects. And when I say by default, I mean that I'm not going to straitjacket the programmer into requiring determinism. If there are non-deterministic algorithms that the programmer wants to use, I will let them use those, except that they have to be explicit. And my language provides for very safe non-determinism. Again, with these non-deterministic constructs, I get data race freedom, I get strong isolation, serializability, and composability. Okay, so very, very disciplined kind of non-determinism. And as I said, this simplifies test, debug, composability, maintainability, etc. Okay? So that's what you can get. I'm going to show you that. That's what you can get through explicit side effects from the programming side. The cool thing is that you can use the same sort of programming model to drive efficiency gains on the hardware side. Okay? So from the hardware side, you can actually build more power, complexity, and performance efficient hardware. You can simplify coherence and consistency because you have a lot of information from the program. You have a lot of guarantees from the program. You can use them to drive the hardware. You can optimize communication and storage layout and essentially have a memory hierarchy that's driven by these explicit effects rather than this random notion of a cache line and crazy, everything can be shared and communicated everywhere and anytime. So you can actually have a simple programming model and power, complexity, and performance efficient scalable hardware. Okay, so this is what I'm going to try and sort of get across to you in the next 10 or so minutes that I have. Okay, so again, our approach. So the general philosophy is to have these structured, disciplined languages. Our take on this are these two projects. The first one, Deterministic Parallel Java, that's led by Vikram Adve et al. Gets rid of data races, again, determinism by default, safe non-determinism, etc. And the de novo hardware project that I'm leading that simplifies coherence, consistency, and so on. Now, I should point out that these two projects are independent. So the DPJ, the Deterministic Parallel Java project, doesn't require all the hardware tricks. The hardware project is inspired by DPJ, but it could work with other language constructs as well. Okay, so you should view them as two examples of a driving philosophy that I just presented. Okay, so I'm just going to be able to give you quick overviews of these projects in the time that I have. For DPJ, essentially, what the main it's essentially an extension of sequential Java, and there's nothing special about Java. We're working on DP C++ as well. So the first aspect about DPJ is that it has very structured parallel control. This is very similar to Silk, TBB, for example. This is not new. It's a nested fork join kind of model. The novel part of DPJ is a region-based type and effect system that I will describe on the next slide. Okay, and this is a completely compile time-based approach. So there's no runtime overhead, and we've evaluated this on a bunch of applications, and the speed ups that we get are close to handwritten Java programs. Okay, so we've evaluated this on irregular dynamic parallelism, array-based parallelism, and so on. We've also shown that we can provide discipline support for non-deterministic code. We have a semi-automatic tool to help with the annotations that are required, and we also can deal with some unchecked code and the software is available on the web. Okay, so the main thing, as I said, was this novel region and type region-based type and effect system that I will quickly try and describe next. So essentially, DPJ has a concept of a region, which is simply a name for a set of memory locations. Okay, the programmer is required to assign a region for every field and array cell, every location in the heap. Okay, so think about these regions partitioning the heap or coloring the heap. Every location has some sort of color to it. Okay, along with these regions, which are essentially type declarations for every memory location, the programmer is also required to summarize the effect on every method body. So what this is saying is, this method body, what region is it reading or writing? The programmer is required to say that. Okay. The compiler then checks that the region types are consistent, the effect summaries are correct. It's always easier to check than to infer, right? So, and this is a simple modular type checking. There's no interprocedural analysis or anything like that. And using these checks, the compiler can then infer whether two concurrent methods conflict with each other or not, whether there is a race between them or not. Okay, if there is a race, that means that the program will not type check. So basically, a type check program, a correct program in this language, is data race free and is deterministic. Okay. The side benefit is that the regions and effects are valuable documentation. So you might say, well, you know, the program has to write all these annotations. Isn't that a burden? Well, yes, it's a burden, but it's only a burden to the extent that the programmer is documenting a reasoning that they have to do anyway to prove to themselves that the program is correct. Okay, and later, people coming in later in the project have that documentation available. They don't have to guess the side effects of these methods. They're documented for you, right? Moreover, for testing, it's a deterministic program. For a given input, you just have to test it once. One until leaving is all you need to test. Right, because you will always get the same output. It is a deterministic piece of code, right? So even though the initial upfront burden for annotation may exist, you have the documentation, which is good for maintainability and so on, and testing is a lot easier. Okay. So here's a very simple example that I will talk about just to show how DPJ, the type system, works. So we have this pair class up here. Okay, it has two fields, 1 and 2. We declare two regions, a blue region and a red region. 1 is in the blue region, and 2 is in the red region. Okay, that's just indicated here. 1 in 1 and 2 in 2. Okay, so this is just declaring the region names, and that's it. Next, we see that for each method, this is a method that sets 1. All we say is that this method writes 1. Okay, it's writing the blue region. This method here is setting 2. It's writing the red region. So we have to put that annotation in, and that's it. That was so the less interesting part. Here's a slightly more interesting part. Here's where we have a co-begin statement to start a parallel phase. Okay, the co-begin results in expresses once calls the method set1, calls the method set2. Okay, for this particular method set1 and 2, we say that it writes 1 and writes 2. Now the compiler infers, okay, the compiler infers that set1, okay, it knows that set1 writes 1. It writes the blue region because that effect was given when the programmer wrote the method set1. The compiler knows that set2 writes only the red region. So the compiler can now infer that when set1 and set2 are called concurrently, there is no conflict because one of them writes a blue region and another writes a red region, and they don't conflict. Okay? And so there are no data races in this program, and it is deterministic. Okay, so this, yeah, are we? 5 minutes, yeah, okay. So this is, this was a simple piece of code, and with this goes, we can express trees with this, we can express non-deterministic patterns with this. The point I want to make here is that this type of disciplined approach where we are describing all the side effects, where, what is written where and regions and so on, gives us deterministic semantics, no runtime overhead. Okay, so that was DPJ, and the exact same annotations that we use for safety guarantees for clean semantics at the programming language level, we can then use them in hardware. Okay, the same annotations can then be used to drive more efficient kind of hardware, and that's the de novo project. And so far we've used the DPJ annotations, but conceptually, the final end goal is to create an ISA level specification that is language oblivious, that basically says, okay, what type of ISA level information you need to express the side effects that will help us build more efficient cache coherent and consistency based systems. So I don't have time to go over this in too much detail, but I would like to just summarize the key insights. Okay, so just focusing on cache coherence and consistency. Okay, just focusing on that. If you look at what systems do today, they have directory-based cache coherence schemes. They are very, very complex. They have many transient states, and it takes forever to verify them. Once they're verified, then designers don't want to reopen them, to change them, to put more optimizations because you have to verify them from scratch. It's completely not extensible. If you look at why, the reason for this complexity, it is that you have races in these systems. Okay, these hardware systems are written to handle races. If your language gets rid of races, then your hardware doesn't have to deal with races. Okay, so we have designed a system, a cache coherence protocol, where there are no transient states. Okay, because we exploit the annotations that DPJ gives us, and it is very, very simple to verify that protocol, like orders of magnitude simpler verification. Directory protocols have huge storage overheads. We don't have that in our protocol. They have lots of performance and power inefficiencies. You have all these invalidations, acknowledgements, false sharing, and so on, and we don't have any of that in our protocol. So overall, our results basically show that when we compare the de novo protocol with a standard messy protocol, we verified it using the Murphy model checker, and we found 15x fewer reachable states. Okay, it's 20x faster to model check. Extensibility, we put some optimizations in. We didn't have to touch the protocol. It was just completely extensible. Storage overhead, we have no storage overhead. After about a few tens of cores, we completely beat messy in terms of storage overhead and scale beyond, whereas messy is generally, unless you're super smart, it's unscalable. We found up to 73% reduction in memory stall time and up to 70% reduction in the network traffic. So our results so far are extremely promising. I am not going to go through all of the detail, and just conclude that the current way to specify shared memory semantics is fundamentally broken. Best we can do is SC for data race 3 programs, but that's not good enough because we can't hide from programs with data races. There's mismatched hardware software. What we need is higher level discipline models that enforce the discipline and hardware that's co-designed with this. And that's what we're doing at Illinois right now, both in terms of hardware and software. So I'll take questions. So I guess I should ask the remote people first. If you have any questions, I'll be happy to take those. No questions. It can't be so crystal clear.
I have a question.
Yeah.
I'm not sure whether you are able to hear it or not.
Yeah, I'm able to hear.
I just wanted to know, what do you exactly mean by explicit side effect? Is it the software developed coherence, or is it something else?
Yes.
Or can you give a small example to illustrate it?
Right. So for the explicit side effects from the language point of view, as I said, those region and effect summaries, right? The effect summaries that I talked about. So when I had the this example here, right? The
Actually, we are not able to see the slides properly, the examples.
oops.
That's why I missed it probably.
Okay, so can you see this slide or no? You see the rights 1 and rights 2?
We see it very fuzzy actually, so we are not able to see exactly.
Well, yeah, maybe I can answer this tomorrow when I come there. If you couldn't see the slides, then I'm kind of at a loss. Yeah, so basically, let me just, a simple answer is the programmer actually puts in a summary of the regions of the heap that are read or written by a given method, right? So that is the side effect, right? That's what the method does, okay? It's a region-based specification of the side effect. And that's what the compiler uses and the hardware uses. I mean, and for hardware, that needs to get translated into something that the hardware understands, but I didn't get into that, but that's what it is. Yeah.
So every process has its own memory.
Every what?
Every process has its own memory.
Every process, what its own memory? I don't know.
Declares.
Declares its own memory. Well, you should think. No, so this is shared memory. Think about this like you're writing a sequential Java or C++ program, okay? Except that there are a few parallel constructs, like the co-begin here, or you might want a parallel for loop or whatever. So structured parallel control constructs, and then these region and effect declarations. Okay, so it's a shared memory heap.
Right.
Okay.
So I mean, in message passing, of course, we don't run into these problems. We run into different problems.
That's right. In message passing, you run into different problems, which is why at about halfway through the talk, I asked the question, should we banish shared memory, right? But if you talk to a lot of programmers, they really, really want shared memory because of the global address space. There are many, many things that they want to do that that is enabled by a global address space, and writing message passing programs requires jumping through too many hoops. Yeah.
Are you
Any other questions?
actually building hardware, or is this simulations?
So right now it's simulations. But somebody's offered to put this on an FPGA, and we'll see where that goes. Yeah.
So is the programmer responsible for creating those annotations?
Yes. So so the first order of the answer is yes. The program is responsible for creating those annotations. Of course, the compiler is going to check the annotations for correctness. That's the whole point of this. But the second thing is that Vikram and people in the software engineering group at Illinois are working on automated inference of these annotations with the programmer in the loop, not completely automated. So for the effect annotations, there's already a paper in the ASC, which is a software engineering conference, that has been very successful at inferring effects automatically. For region annotations, they're still working on that. Okay, so the idea is that you get some help from automated tools. Yeah.
So that'll handle the case where your last method, the void set1 you have to annotate with the regions that the methods that it calls, right, are writing. So if I have a hierarchical structure there, right, does that expand, and I as a programmer have to put all the annotations?
Yes, so that's a very good point. But think about it, right? So what this is saying is that set1, 2, right? So if I as a programmer, okay, I'm calling set1 and set2, I should know what regions those things are accessing.
Right, but my question is that set 1 and set 2 may then in turn call
Correct.
some other methods
Correct.
that go farther down. So I, as a programmer, do have to keep track of that whole hierarchy of regions.
Well,
that could be
keep track
modified.
means because I may not have written all that stuff, right? That could be some library, somebody else wrote it, right?
Yeah.
However, so this part is inferred. This is inferred by without any tools. That's the whole point. Because over here, and I know the remote guys can't see this pointer, but over here, right? When I say void set 1, which was in the previous slide, right? I wrote writes 1, or somebody wrote writes 1. Whoever
Right.
defined set 1 wrote writes 1.
Yes.
Right, so I know I as a programmer have this as an interface, right? So if I call set 1, the interface for set 1 is that it writes 1. So I know that, and then I as a programmer am responsible to move that up there, if that's what you're asking.
But I don't. But if set 1 calls something else.
Yeah,
right,
so that would be written up here.
that would, and it would not be.
Whoever wrote set 1
Okay.
would have written that up here.
So I don't have to fold it up
I as
to
a
this
programmer
write set
don't
1
have to
too.
dive deep,
Okay.
which is why
Okay, that's what I was asking.
which is why the compiler doesn't need
Right.
interprocedural analysis, and it's a
Right.
simple type checking system. Exactly. That's a very good point. Yeah.
Is there a reason your inference can't like bubble the writes 1 up? So for example, like in that actual method, you said
This-
writes 1, writes 2.
Here or up
No,
here?
the third one, yeah.
Yeah.
So why is there a need for that if the compiler can just look at set 1 and set 2 and notice that they write 1 and 2?
Because of what Alvi just said. Because the compiler does not want to, if set 1, so the compiler infers this writes 1 only because this set 1 said writes 1. The compiler is not looking inside set 1 to figure out that it writes 1.
No, what I'm saying is why do you even have to say writes 1 up at the method signature for set 1, 2? So set 1,
Because
2
somebody else could call set 1 too.
I
Right?
see, I see. So it's for the
Yeah.
purpose of the previous
It's just
guy.
the pairwise.
Yeah.
It's between the levels of the hierarchy. that you
Yeah,
need to
this is
specify.
the interface for set 1 2.
Yeah.
It's the side effects
Yeah.
of set 1 2.
Right.
I see, I
Right?
see.
And I do not want to have to look inside set 1 2 to figure that out.
Right.
Right? And when somebody else calls set 1 2, they don't want to look inside set 1 2 to figure that out. It's sort of natural if you think about it, right?
Yeah.
So you've added the notion of regions and effects.
Yeah.
Is that sufficient? Would it help you to have? Is there anything else that you would like to add
I'd
discipline-wise?
love other people, do the research and figure this out. Yeah. I don't know. From
Well,
a program.
How did you settle on this? I guess.
How did we settle on this? So actually the question would be, all right, let me give you sort of some nuances here, right? So one thing is that for the non-deterministic stuff, we have to extend our effects, okay? Even for the deterministic stuff, it was an exploration, it was an empirical kind of a thing, looking at different programming patterns, right? And seeing what kind of effects we would need, right? So there is that nuance that, what kind of effects are you using, right? Is writes and reads good enough, right? Okay, so we don't know. I mean, this is what sort of seemed to work well for a large class of applications. There's another kind of effect that I didn't talk about, commutative effect, and who knows, right? That's for exploration. But then the deeper other aspect of your question is this type of static, more or less static? These types are parameterized, but still, is this general enough, right? There's a downside to there's a minus to everything. So the question is this really general enough? We do know patterns where we have to change, that pattern to actually fit into this, right? If you have if your patterns change in certain ways dynamically, and there are certain things we can't express in this, right? Are there other general ways of doing it? Probably, right? So we have someone else working at Illinois, and Bikram's collaborating with them, where they're looking at theorem provers, formal methods, verification techniques to check for annotation, more general annotations, right, than just this, right? So they have annotations that use more complex kind of relationships, right? So it's all researchy, yeah. That's it. Who?
One thing I want to mention is that when your cameraman shot your screen a couple of minutes ago, we had a sort of a blue trapezoidal-ish screen. That actually looked better.
Thanks for the feedback.
Okay.
Glenn?
Sure, I'll ask. So these regions, are they per instance or per class?
Per instance. So I didn't get to the more complex.
Okay, because otherwise,
So this is a tree, right? Every node in this, every field is a different region because it's parameterizable. So, you know, the upper one is root, okay? Then it's, I mean, X is the root, X colon L is the left guy, X colon R is the right guy, X colon L is this guy, X colon L colon R is that guy. You can just, you know, you can write it in a recursive way. Okay, so you can actually, this is a recursive parallel code where the parallelism is coming from, you know, individual nodes, and each of these is a separate region. And
so when I create an instance of tree, I don't have to know about the internal regions defined within the class, or I do?
say that again.
So if I define a tree, do I have to know about regions L and R?
Yeah, because here this is the declaration of the tree. Okay, so all you need to know, you're just parameterizing the left, you're just naming the left, when you declare the left pointer, you need to give a region name to it, right? So the region name, for every field in your node, you need a region name, right? So the region name here is P colon L because P is the name of is the parameterized instance, right, of this region, okay? And then the right is P colon R. And then when you're incrementing, let's say, you know, the whole tree, then that's you're writing the whole P, so it's P colon star. Again, this is recursive, so when you call P colon L, then you're incrementing the left side of the tree. That's all. So it takes a few, you know, I haven't done a good enough job explaining it, but it's not that complicated.
I think we'll let some questions.
In a particular region, you have a default region for everything else?
Yeah, sure, yeah.
All right, well, if you have any other questions locally, we can grab Sarita afterwards briefly. Otherwise,
Okay, thank you.